Hello class, in this video we will resume where we stopped last time. So last time I asked you to study the motion of a horizontal elastic pendulum. When we say we want to study the motion of something, what we're exactly doing? We are trying to find the equation of motion. Our way to find the equation of motion of this horizontal elastic pendulum is by using the conservation of mechanical energy. Okay, so let's start together. First, just to give you a small note, a horizontal elastic pendulum is simply a spring block system. It's a spring and block system, so it's a spring block system. Okay, so we start with figure A. We have our spring and the block. So what are the constants that we're talking about? We have a spring of spring constant K, right? We have a spring of spring constant spring. It has a spring constant K, and we have a block of mass M. And at first, the spring and the block are at the equilibrium position. This one here is the equilibrium position. It is when the spring is at its natural, so the spring is at its natural length. So the natural length of the spring. Okay? At first, we extend or we shift the spring from point O to point A. Okay, we shifted from point O to point A. And this shift is denoted by xm. So we shifted a distance xm. Here's xm. It is from point O to point A, and point O is the equilibrium position. And then, after shifting it, we release it without initial velocity, and the spring or the block will continue its motion. It will compress, then expand, compress and expand, passing through the equilibrium position. Okay? And for our study, we will assume that we have no friction and no air resistance. So no air resistance, so the mechanical or mechanical energy is conserved. Okay? So again, we have our spring block. The spring is of spring constant K, the block is of mass M, and we expand or we shift the spring distance xm, and the spring will move in this direction. It will compress, then it will expand, and so on and so forth. And because we have no friction, it will continue this motion until forever. Okay, now let's start by studying the energy of the spring at T. So we'll study, let's go down a bit. So let's start studying the energy of the spring at T equals to 0, or at T0. At T0, which is the instant where we had the, at T0 it is at point A, where it is the instant where we shifted the spring from its natural length. And when we shift the spring from its natural length, what are the energies, or what is the energy of this spring? So, and the spring and the block, I'm sorry. So EM equals E potential plus E kinetic. But we have no kinetic energy because we released it from rest, so that's 0. And E potential, do we have any gravitational potential energy? We can take this line as the reference, so we will end up with no gravitational potential energy. What we have is the elastic potential energy, that is equal to half, that's equal to half K xm squared, right? Do we have any other type of energy? No, we don't have anything, because gravitational we don't have, kinetic we don't actually have because it's released from rest. What we only have is the elastic potential energy. So I'm going to write it here again. EM at point A equals half kxm squared. Choose this color here. Okay. Now let's see at any time t. So at any time t. At any time t, we mean at any time during the motion of this block. So it could be here, 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 at any position. Okay? At any, not exactly at the fully compressed position, point B. Okay? So at any time t, E mechanical would be also E potential plus E kinetic. At any time t, it does have some velocity, okay? Because it's here, it's either going this direction or this direction, so it does have some velocity. We will call this velocity V, okay? So half, and it does have some velocity and also does have some compression or expansion. So it's either somewhere around here, it does have some compression, some expansion, or somewhere around here it does have some compression. Okay? And we call this compression or expansion just x, which is x of this. It could either be, let's say, plus x from here or minus x from here. It depends, because this is our axis. This is y and this is x. Okay, it could be any point x positive or x negative. I hope everything is clear. Now let's continue. So half k x squared, x is any x, plus half mv squared. Okay? Now let's continue. So we know that at t equals to 0, we have E mechanical at point A is half kxm squared. Now let's do the same here. So EM at any time t equals, it's not gonna fit inside here. Let's shift it a bit. Let's put it here. Yeah. So equals half k x squared plus half mv squared. Okay, let's put a rectangle around it. It's not a very nice rectangle. Let's fix this rectangle. This is better. Okay, so the E mechanical at point A is half k xm square. Xm is a constant because we already chose xm. It is the distance we shifted the spring from its equilibrium position. X, on the other hand, is a variable. So x is the position, it's any position of the block between the maximum expansion and the maximum compression, or the minimum, we can say. But it's like the maximum compression and the maximum expansion. X is any point. So X here is dependent on time. So X actually is not really just X. It's X in terms of time. Okay? And if X is in terms of time, for sure, we're talking about also a VT, because we know that x is, or v, the velocity, is the derivative of x with respect to time. Anyways, I want you to keep this in your mind. Let's move. So this is E mechanical at A, E mechanical at T, and we know that the E mechanical is conserved. Thus, we can say that, let's choose another color, EM at A equals E mechanical at any time t. At A that's actually at t equals to 0. Okay? So half k xm squared equals to half k x squared plus half mv squared. Okay? Now, what I want you to do is that we're going to take this expression here. So this expression, I'm going to take it and study it. I want you to study this part here. So this part here consists of a half k, which is the spring constant, and xm squared. As we said, xm is a constant value, so all this expression here is constant, right? Whereas this part here, we said that x is dependent on time and v is also dependent on time, so this part here is not constant and it is time dependent. Okay? So let's write it down in a better way. This part here is a constant. This time here is time, or this part here is time dependent. Okay? What we're gonna do next is we are going to derive both parts or both sides with respect to time.